So this type of problem has come up frequently in our work this year. So it's finding a certain term, which we're going to call the nth term. It might be the 7th term, the 12th term, the 31st term, but finding a specific term in an arithmetic sequence. So before we go on, I just want to talk about an arithmetic sequence. So a sequence is just a string of numbers. But usually it follows a pattern. And an arithmetic sequence, again, it's spelled the same way as arithmetic, but it's pronounced arithmetic, all right? So in an arithmetic sequence, they follow a specific pattern. So for example, maybe it's 2, 8, 14, 20, 26, 32, and so forth. The pattern here is that each time we get from one term, this is the first term, the second term, the third term, each time we get from one term to the next, we have to add or subtract the same number. So in this case, we're adding 6. To get from 8 to 14, we add 6. To get from 14 to 20, we add 6. To get from 20 to 26, we add 6. From 26 to 32, we add 6, and so forth. So it always follows the same pattern. It's not always going to be plus 6. It could be minus 3 or plus 11 or minus 14 or something like that. But it's always going to be adding or subtracting the same number, right? So that's what makes a sequence arithmetic. Just to contrast that with other types of sequence, another type is geometric. And that would be something like 3, 6, 12, 24, 48, 96, and so forth. In this one, if we said, oh, maybe this is arithmetic, maybe that's the same way, here we would add 3, but then we would have to add 6, and we would have to add 12. So we're not adding the same amount each time. In geometric, we're always going to get from one term to the next by multiplying or dividing by a certain number. So this would be times 2. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. 48 times 2 is 96. Right? So that is a type called geometric. There are other sequences that are not either arithmetic or geometric. Take, for example, if you did 1, 4, 9, 16, 25, 25, 36, 49. This definitely follows a pattern. If you remember from your memory work, these are all perfect squares. So this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, and so forth. You can tell what's going to come next. It's appropriate for me to put dot, dot, dot because the pattern is obvious. We're just going to keep writing what the squares are. But they don't always increase by the same amount. If I do 1 plus 3, I get 4, but 4 plus 3 is not 9. It doesn't increase in a geometric way, or it doesn't change in a geometric way. If I do 1 times 4, I get 4, but then if I try and do 4 times 4, I don't get 9. So this is still a sequence. It follows a nice pattern, but it's not arithmetic, where it's increasing by adding or subtracting, or it's changing by adding or subtracting a number. It's not geometric, where it's not multiplying or dividing by the same number. It's still a sequence, but it doesn't have that adjective in front, arithmetic or geometric. Okay, so that is what we're talking about when we're talking about arithmetic sequences, specifically this type where we add or subtract the same amount to get from one term to the next. Then what we want to do is find a specific term. So let's go back to this example, and I say, all right, 1, 2, 3, 4, 5, 6. I know the first 6 terms. So suppose I asked you to find the 10th term. Well, you might say, oh, that's easy. I'm just going to go and keep adding. If this is the 6th term, then 7th, 8th, 9th, 10th. I'll just do this 4 more times. So then I would get 38 and 44 and 50 and 56. There, this is the 10th term. Okay, that's fine, except what if I ask you to find the 57th term? You're not going to want to do this 57 times, or I guess another 47 times since we're at the 10th one. You're not going to want to do that many times to get to that sequence, or to that term in the sequence. So this is where our formula comes in. But before we do that, let's just talk about what we would do. Again, these are each of our terms. Our sequence is defined by where we start and how far our jumps are. All right, so we start at 2. The sequence would be completely different if we decided to start at 7 or 4 or 1 instead. So our starting point is significant, and then how far we jump to get from one term to the next is significant. If we decided to start at 2, but instead we jumped 7 each time we moved, that would change the sequence. So a sequence, an arithmetic sequence, is defined by where it starts and how far you jump. Right? So to get to, let's say, the 10th term for right now, we want to know, well, how many jumps did we take and how far was each jump and where were we starting from? So for example, here, to get to the 10th term, we had to make 1, 2, 3, 4, 5, 6, 7, 8, 9 jumps. So to the 10th term, there were 9 jumps. That is not coincidental that to get to the 10th term, we did 1 less jump than the term number. Again, we're starting from here. There was no jump to get to that one. That was our beginning point. So there's always 1 less than how many terms there are in terms of the number of jumps, right? And then each jump was worth 6, and then we started at 2. So let me show you what the formula is. It's L, and I'm doing that in cursive because otherwise it would look like a 1. You could also do a capital L if you wanted, if you don't like cursive L's. A plus n minus 1 times D. All right, and let me go say that what this is. Our formula in our book uses L here. That's not what most people use, but we're going to use it. This is the last term. That's what the L stands for. Technically, sequences go on forever because they follow a pattern, but when we say the last term, really this is the term we're trying to find. Okay. A stands for the first term. And again, if you were to watch a different video about this, they would probably call it something else. They would probably call it A sub 1, meaning the first term, all right? But we're just going to call it A for the first term. D stands for, it's called the common difference. In other words, how much space is between each of the two terms. So if I were to take 8 minus 2, the larger minus the smaller, their difference is 6, all right? If I were to take 14 minus 8, the larger minus the smaller, their difference is 6, and so forth. So really, this is how big is the jump. All right. N minus 1, N stands for the term number we're trying to find, or the number of the term. So again, this might be the 10th term, or the 14th term, or the 3rd term. So N stands for the number of the term that we're finding. So then n minus 1 is really how many jumps have we done? All right. Okay, so then let's do this. Let's find, I think the number I said was the 57th term. So what is the 57th term? Of the sequence 2, 8, 14, 20, 26, 32, 38, and so forth. Okay, so let's write down our formula. L equals A plus N minus 1 times D. And again, I just want to say back up here, again, we talk about where we're starting, right there, that's the A. So in our case, it's the 2. How far is each jump and how many jumps are we going to take? That's going to tell us how we get to a specific term. Where did we start? How far did we jump? And how many jumps are we making? All right, those three things together are going to get us to any term that we want. So in this particular case, our first term, actually L is, we're trying to find the 57th term. So this is going to represent the 57th term. A is where are we starting, so our sequence starts at 2. All right. The common difference, how far is it from one term to the next, is 6. And then this right here is telling us that we want to find, this is asking us how many jumps are we going to make. So it's the number of the term that we want to find, which is the 57th term minus 1. We're always making one less jump than the term we want to get to. Now, sometimes people say, well, I know that this is going to be 56 because if I'm looking for the 57th term, I just want one less. You could write this just as 2 plus 56 times 6 and not worry about doing the 57 minus 1. If you don't want to, you can just do that right away. That's fine. All right, or you could write it and then this would be your next step. So I guess what I'm saying is you could skip writing this out and just go directly to this. Okay, then order of operations tells us that we have to do multiplication before addition. So the first thing we're going to do is not the 56 plus 2. Don't do that. It's tempting, but don't. Do this first. All right, so 56 times 6. 6 times 6 is 36. That's 33. So then we've got 2 plus 336. All right, there's no choice. The only operation left is addition. So this is going to be 338. And that tells us that the 57th term is 338. All right, now if you think, well, I'm not sure that I totally believe you, let's go back and do it again, but this time let's do it for the 10th term, just so that you can see that we actually get that when we use the formula. So if we were to do this again for the 10th term, our formula again is A times N plus N minus 1 times D. So A is 2. Since we're going to the 10th term, we're going to do one less jump, so this is going to be 9. So either you could write 10 minus 1, or you could just say, I know I need 9 jumps, times the size of each jump, which was 6. All right, order of operations says do this first. Oops. I don't know why I put A instead of 2. This is 54, so we've got 2 plus 54, and 2 plus 54 is 56. And that is exactly what we found when we did it without using the formula. All right, so there's one like this in the workbook on page 74, and it is problem number 5. So if you would like to practice one, that would be a good place to go. All right, thanks a lot. Bye.